Okay, guys, so in this video, we want to talk about another application of exponential functions, and this is compound interest. There are two of them. One is the general compound interest formula. And again, we could set this equal to A of t, and that means the account balance is equal to the initial amount present times the quantity 1 plus r over n, where r is the interest rate as a decimal, n is the number of compoundings per year. Notice it's up here in the exponent as well, and t is the number of years. So that is for a finite number of compoundings per year. The continuously compounded interest formula is A equals, and I like to just say PERT, P times e to the RT, where P is the initial amount that you deposited, E is the number E, R represents the interest rate as a decimal, and T is the number of years. So let's check out an example. Determine how much time is required for an investment to quadruple in value if the interest is earned at a rate of 6.25% compounded monthly or continuously. So here's what we have. We have A equals P times 1 plus R over N to the NT. And then we have A equals P e to the RT. The first one would be for monthly compounded interest, and then the second one is continuous compounded. Notice in this problem, they never told you the initial amount present, but they did tell you that it quadruples. So it actually doesn't matter, because whatever the initial amount present was, the current amount is going to be 4 times the initial amount. So I can put 4p in here, okay, instead of the account balance, because I know that whatever the initial amount was, it's denoted with p. When it quadruples, it's going to be 4 times that. Then if I start solving this equation, I can just cancel the p's off of both sides. Okay, now let's fill some other things in. So this one would be 4 equals 1 plus r, which is 0.0625. Be careful, you have to convert it to the percent to a decimal. And n is the number of compoundings, which if it's compounded monthly, that would be 12 compoundings per year. And you would have 12t here. Okay, this one would be 4 equals e to the 0.625t. Okay, so now what I'm going to do is I'm going to use Desmos to solve this pretty quickly. So this was an old problem I had in here. What I'm first going to do is graph the equation y equals 4, because that's what I want either of these equations to be set equal to. Then this one I'm going to have as y equals 1 plus 0.0625 divided by 12 to the 12x power. I'm going to use x as the variable. And then this one is y equals, I'm going to do this equation, e to the 0.0625. I forgot to put the 0 right there, so be careful of that, x. Okay, and now if I turn this off, it looks like the blue one and the green one are right on top of each other, and they're pretty close. But what I'm going to do is solve for the intersection point where those are both equal to 4. And as I begin to zoom in, you'll see that they do not actually intersect at the same spot. The green line intersects at 2.181. So this would be for the exponential, t equals 22.181 years. And the monthly compounded would be 22.238. And I'll just tell you, in general, continuous compounding is always going to be faster than any other type of compound interest, whether it's yearly, monthly, weekly, daily, by the hour. Eventually, it's always going to be a little bit better. Here, it doesn't make that much of a difference. It's not even like not even a tenth of a year, but it does make a difference, which if you're dealing with lots and lots of money, that could be a very significant difference there. Okay. All right, guys, that's compound interest for you. Hope that was helpful. Take care.